I'm a lab bench scientist who moved into science, technology, and society, or science studies. And my work is really focused on the governance of emerging technologies. And I've been studying and working with the synthetic biology community now in the US, or in the UK and Europe, and then for the past 10 years in the US, through a variety of projects, some of which have been collaborative with scientists and engineers, and others of which are sort of grounded in the social sciences. But even the social science grants, none of them have involved never engaging with or interacting with or building relationships with synthetic biology practitioners. So the work that I'm going to share with you today really comes out of two social science-led grants. So this Engineering Life project that Robin mentioned was a sort of starting point where I got interested in the topic. And then more recently, I've got a grant to sort of study this work. Before I jump in, just sort of situate again. Within the governance of emerging technologies, one of the things I'm particularly interested in is infrastructure. And the field of synthetic biology, kind of relatively new field, sort of 20, 25 years old. And because of that, it has been a field particularly preoccupied and concerned with trying to build infrastructure, right, to become a field. And so we've seen a lot of effort being put into things like standards and databases and training programs and research centers. And what I'm going to talk about today, DNA foundries and sort of biofabrication facilities. So this is something that I sort of saw emerge once I had sort of been a sort of participant and observer in the field for a while. Now, just to kind of give you a quick sense of why I might be interested in infrastructure, right? Because infrastructure can seem like something pretty mundane or boring, but I see infrastructure as a world-building activity, right? So building infrastructure involves having a sense or a view or making a prediction or a hypothesis about how the world should be, what you think the world should look like, and then working to design that world into material form, right? So it involves making these predictions and trying to build them. So we can see here, this is just a picture, for example, of the Edinburgh Genome Foundry, right? This is a form of infrastructure that really involved making lots of choices, right? How do we think we should do biological engineering? What kind of equipment do we need? Where are we going to position the equipment? What kind of robotic arms are we going to use? All that kind of, how do we configure it, right? So it's really about trying to sort of embody your aspirations for the future. And in that sense, too, infrastructure involves a myriad of design choices, right? But inevitably, the choices that you make, the design choices that you make, end up shaping the kinds of questions that you can ask, the kinds of data you can collect, and then the range of possible outcomes, right? So just to talk, very briefly with Biofoundries, you need to design your facility differently if you're going to work with bacteria versus mammalian cells, for example, right? So decisions that you make early on are going to have consequences for the kind of work that you can do. And so it's particularly interesting as a sort of sociologist or anthropologist to look at the design choices that are being made, but also contestation over design choices, because those can reveal different kind of visions of the future and how they might be manifest in infrastructure. And in that way, I think studying infrastructure is deeply connected to these questions of governance. So just to kind of give you that sense of why I'm interested in this, is that if you study these design choices in the making, you can help to identify choice points and potential options for governance to kind of build the sorts of infrastructures that you want to see happen in the, that you want to see working in the future with that clear vision of what that future might be and how you would get there. So the infrastructure or the facilities that I thought I would share with you a little bit about today are these biofoundries or biofabrication facilities. Does anybody work in a biofabrication facility or have worked in a biofabrication facility? Biofab? A couple of people. Okay, so we'll see how familiar some of this is to you. Anybody not familiar or haven't heard of biofoundries? Okay, there's a few. Okay, so these are a few images just to kind of begin to situate you, but obviously I'll sort of talk about it, kind of walk you through some of it over the course of the seminar. But these are sort of intended to be high throughput, increasingly automated facilities for genetic design and construction, right? So the idea is really to sort of really try and embody the design, build, test cycle, where you can really develop the tools to, in a sort of massively parallel high throughput way, explore the design space for synthetic biology and design and build and test multiple constructs and strains to get you the kinds of organisms or molecules and things that you want. So over the past, the biofoundries kind of emerged, I would say, around the late 2000s, early 2010s. In both academic and commercial settings. So there's now a group called the Global Biofoundries Alliance, which is a cluster of academic biofoundries around the world. So Europe, Asia, and North America in particular. Right now, there are about 40 members of this alliance. So it kind of shows you the scope. There's about, sort of 3 or 4 dozen biofoundries. I'm guessing another 5 biofoundries are about to join because in August of last year, the NSF announced a further 5 biofoundries that they were funding, each to the tune of about $25 million. So this is sort of, there's continued interest in this type of facility and what it can do and what it can bring to the table. So that's kind of the academic side. There have also been some startup companies that have built themselves around a biofoundry model, which is often presented as a kind of platform model. I'll talk a little bit about that. These are 3 of the sort of big US well-known companies that all of them kind of spun out of academia. And they all took the sort of bold step of going public, right? So Amyris founded 22 years ago. Ginkgo Bioworks spun out of MIT, so close to home, and is still in Seaport here. And then Zymergen, which is kind of spun out of Amyris. But interestingly, what you can see here is that both Amyris and Zymergen in the past couple of years have declared bankruptcy. Last year also, Ginkgo Bioworks did kind of a big downsizing and restructuring. And I say this I'm not going to go into detail about this per se, but to say that what that suggests at this point is that these commercial facilities, we'll talk about this in the context of academic facilities too, have yet to kind of crack that value proposition, right? Yet to figure out exactly how to create that sustainable value. So this is a challenge, I think, to kind of think through, and it's worth kind of spending time trying to understand what some of those challenges are. So the way I thought I might set this out, kind of thinking through 3 kind of big areas for this, for what I'll share with you today. Thinking about some of the visions and aspirations that sit behind biofoundries that you regularly hear invoked for justifying and thinking through what their goals are. And thinking about, so kind of 3 themes that I think emerge kind of quite regularly in this case are scale, time, and work. So what I mean by that, I'll give you some examples of the sorts of visions and justifications we see behind these biofoundries. So scale is a big one. We'll spend a lot of time on it going forward, but the idea that you can scale up genetic construction and testing. So in this, doing kind of increasing the number of the number of samples and the throughput of samples. This is also very closely connected with questions of time. So being able to do not just more samples, but more samples faster than you could do before, right? So there's sort of a scale time thing here. There's also a spatial element to this. Biofoundries are sort of positioning themselves as helping to centralize the work of genetic engineering, right? So making themselves one-stop shops for sort of the design and construction of DNA and of organisms and strains and so on. And this kind of has a lot of, there's a lot of really interesting conversations then that start to happen around what that means for the future of work in biological engineering. So we hear a lot of times about biofoundries really being a key instrument or key facility to help us reduce error and improve the reproducibility of genetic engineering, right? We also hear conversations about de-skilling the work of biological engineering, right? And this is connected with sort of, again, like work-time nexus, the idea of promoting creative freedom. So taking the time and effort away from doing the actual construction and building and testing and freeing up people's mental space to think more about the design questions. What do you want to do? Not the mechanics of how you would do it, right? So these are some of the visions that we hear. And I think taken together, there's this kind of broad push to say that biofoundries are really this kind of catalyst for trying to shift biotechnology from being artisanal to industrial, which is kind of, a big goal of synthetic biology writ large. But biofoundries are a place or a site where these visions are kind of being manifest and worked through. And these are connected. This move from artisanal to industrial, this is where this bioeconomy angle comes in as well, right? So this is really, the shift to industrial is also then linked with broader sort of social, political, geopolitical concerns around using biology and biotechnology to move us away from a fossil fuel dependent economy to a more biologically based one. And if we're going to do that, we need to be able to produce at industrial scales, right? So biofoundries are sort of this sort of experimental hub, if you like, for trying to think through that kind of work and how we might get ourselves into this kind of more industrialized, but also more bio-based economy. So again, I think this is a bioeconomy seminar, right? So I thought I'd try and make a few connections there. So they're pitching themselves as these kind of hubs, right? Hubs for translation across many different units. The biofoundries, especially the academic ones, are often oriented towards academic users, but with the idea that this helps you to kind of fast track your research and build better connections with industry, right? Also taking industry clients, and then there's also commercial biofoundries that are working primarily with industry clients, right? But also as a site where if you're learning how to kind of routinize and standardize and really engineer biology, then you can have an important role to play in kind of integrating or interfacing with policymakers and with standards bodies and so on. So to really figure out, well, how do we actually, what are some of the standards and measurements and things like that we should take into that should kind of be standard across engineering biology to enable trade, to enable integration into value chains and so on. And then there's a few other ways in which I think biofoundries kind of position themselves interestingly in the bioeconomy. So there's a question, I think, for me about the degree to which they're sort of both supporting and trying to disrupt traditional biotech sectors. So we see, for example, I'll pick up on some of the commercial foundries here. Ginkgo Bioworks saying, actually, like in one facility, we're not just working on drugs. We can work on pharma, but we can also work on environmental biotech. We can also work on ag biotech. We can also do consumer-facing products, right? It's a reorientation of how we work, not based on sector, but perhaps, for example, on expertise in engineering particular metabolic pathways. So you can see this, for example, with Amyris saying, well, we work on breakthrough molecules for anti-wrinkle skincare, a zero-calorie sweetener, a life-saving medication, a fine fragrance, or polymers that make electronic circuits more effective, right? Like that's cutting across multiple different sectors. And it should be said, actually, Amyris started off with a major focus on biofuels, right? So they were kind of able to pivot their work increasingly into kind of consumer-based and kind of wellness-based products by becoming experts in engineering particular kinds of metabolic pathways rather than necessarily tying into a particular mode of doing in biotech. So I think there's this kind of question about the degree to which they're both supporting current biotech, but also stand to kind of disrupt the way that biotech sectors are configured. It should be said that most of the products that Amyris is talking about are not necessarily brand new products, but invisible substitutions of existing products, right? And I think this is a really important element of the bioeconomy. I mean, it's, you might say, oh, you should be really kind of groundbreaking and kind of radical, but actually a lot of these invisible substitutions are actually how that kind of transition to a bioeconomy is being framed to start with, right? You still have to integrate into supply chains. You still have to figure out how to produce your, you have to figure out how to produce your products reliably to high standards and so on. And you have to figure out how to disrupt the existing supply chain to make space for your product, right? So I think, all these things together make Biofoundries quite an interesting site for working through some of the challenges. You can start to see within them, as you look at what's going on inside, some of the bigger picture challenges around how you would grow a bioeconomy. So in my work, I've had the chance to go and visit and talk with biofoundries, probably about a dozen now, both academic ones, commercial ones in Europe and in the US, and kind of see each biofoundry as its own design experiment, right? It's really fun. You can do some comparative work because they're all making different choices on how they configure themselves and what they're going after. So there's a certain amount of shared interest. For the most part, there's a kind of fundamental shared investment in building capacities to scale up DNA design and construction, and to some degree strain development and kind of testing. But what we see across these facilities is incredible differences in how this is being pursued right now. Some of it relates to funding. So we're seeing like different degrees of investment in high throughput robotics and software, right? Do you buy all the latest fancy equipment? Probably depends on how big a grant you got or where your funding is coming from, right? How much investment do you put into software? One of the early choices in a foundry is kind of how to configure your workstations. So we've seen some foundries go all in on having these integrated platforms, like the picture I showed you of the Edinburgh Genome Foundry that has these robotic arms, and really like the human puts the sample in and closes the door, and then the system in principle does the rest, right? Versus like individual stations where there's a lot more human involved, or even the kind of reconfigurable stations that Zymergen worked on, where they sort of have these carts that you can snap together in different orders, right? Underpinning this again, so it's like you can dig in. Why would you do this? What are you doing it for? I think there are different imagined relationships between machines and humans, right? Is the focus here on substituting human labor or augmenting human labor in different ways, right? So I like to play this little game. This is the slide I showed you before. You pull up a picture of a biofoundry and you're like, do they have people in their images, right? And as you go around, if you look at different biofoundry websites, you will see those that absolutely kind of like thrive on showing you just the equipment as if this is a sort of self-running, self-driving lab, and those that are very keen to incorporate people into their images, right? But these are different imagined relationships, different pictures of the future that we can see. At the end of the day, I'm going to say that, I mean, biofoundries, I think, are clearly much more than just the machines. The way that I think about them is that they're really trying to pursue a very elaborate choreography, like a reorganizing of how machines or hardware, wetware or biology, software, and humans interact. Right? This is about trying to figure out how to get them to engage and interact with each other in new ways, with data being at the heart of it all, like how that information flows between the various components, right? And that, you know, the idea behind it is if we can only figure out how to do this right, we're going to unlock some new value. We're going to create new value from this, right? So this is kind of a big experiment, ongoing experiment, in how do you configure these elements so as to create value? And it's a challenging one. So we can talk through some of the developments and tensions. I'll bring this back up and kind of talk through some of the things that we're seeing that relate to like challenges and tensions around scale and work and time, kind of within the biofoundry. So the first thing I'll tackle is scale, and I'll start by saying, actually, I think there are many overlapping, slightly conflicting, not necessarily well-aligned meanings of scale that are at play in biofoundries. And it's kind of fun to see how they emerge and how they play out. So I'll try and give you 2 or 3 examples of like different ways in which scale features. And the first one I'll mention is what I call like scaling down to scale up. And it's really about these kind of non-linear transformations across scales. And a really simple way to think about it is this move from the Eppendorf tube or the 96-well plate, right, to the kinds of plates that we increasingly see in biofoundries, which are these like 1,536 well plates, right? Which aren't, I mean, you can't use a standard pipette for them. Instead, you need to buy a several $100,000 robot that will use like acoustics to dispense nanoliters of liquid into the individual wells, right? So you're sort of, what you're doing is you're scaling down the volume of each reaction in order to scale up the number of reactions that you can pursue at any given time. So this is like very parallel, to be able to do parallel testing, right? So scaling down volumes to scale up numbers. And this turns out to be incredibly challenging in both theoretical and conceptual ways. So I'm not sure if anyone here has like tried to do this work, but it's, you know, it's got multiple challenges associated with it. One of which is just trying to translate a standard molecular biology assay into this kind of high throughput miniaturized version is not straightforward. And maybe a good analogy here is baking, right? So if you're going from like a 12-inch cake to a 6-inch cake, you can have all your ingredients, but you can't bake it for the same length of time, right? It's reaction kinetics. And maybe actually it's less about just having the ingredients, but making sure that the ratios of the ingredients, of the salts, of the sugars and the fats and so on are in proportion to give you that tasty cake. So this is actually, you know, requires more than just miniaturizing. It involves understanding at a deep level what's going on and being able to retool your workflow from the bottom up to carry out that work. So there were some sociologists of science back in the late 90s who were looking at the advent of DNA synthesis technology who came to a very similar conclusion, which was they said automation is not simply mechanizing a protocol, but you have to reconceptualize it. It's like from the bottom up, you have to rethink what it is. So that's a lot of the work right now that these foundries are doing. And it's a kind of big practical challenge. But it's also a conceptual challenge for researchers or for clients who are thinking about doing this kind of work. Because if I suddenly tell you like, oh, instead of testing, 12 conditions or so, a dozen conditions, you can now test 200 in a single experiment, right? Your design space has foundationally changed. You have to think about like, what is that new design space? What are those new parameters I would be interested in thinking through? So it's a reconceptualization in multiple ways, right? It's this challenge of scaling down. And then, of course, at the other end, and this isn't something that most of the biofoundries that I've engaged with are really working with in detail yet, is this going from scaling down to scaling up, right? To the sort of small fermentation tanks all the way up to kind of industrial scale. My guess is this is similarly nonlinear in various ways, although there are countries like Japan that have developed great expertise in this, right? So it's not that it's not that it's not possible, it's just that it takes time. Just interestingly, last week, the National Security Commission on Emerging Biotechnologies put out a report and they noted the economic challenge of scaling up. And they talked about this kind of vacuum in between the kind of initial biotech proof of concept development and the industrial kind of manufacturing of it, saying that in that middle space, there's not a lot of funding. I would sort of probably like, in addition to that, say it's not simply an economic case, it's also time and expertise and knowledge that need to be developed too. So the funding is not just linked to building the facilities, but to supporting the long-term investment of building that knowledge, right? Okay, other ways in which scale features. So this is a slightly different version of scale, which is more about accommodating diversity. So scale not in terms of doing the same thing over and over again, but actually in the variety of things that you might be able to do. So this is a picture, this is what you would have seen if you walked into the headquarters of Ginkgo Bioworks down in Seaport in summer of 2022. This is the facility that was set up to do high throughput COVID testing. If you walked into the headquarters the next year, this room has been totally reconfigured because COVID testing was no longer a priority, right? All this is to say that the kind of infrastructure that you design is just a very visual kind of reminder that the kind of infrastructure you design allows you to do certain things, but not other things, right? And so again, this is something that the National Security Commission noted in their report last week, saying that biomanufacturing facilities are not usually optimized to do multiple things at once, right? So you need to retool them if you're going to move from making vaccines to making chemicals. So again, we need to think about this. Then starts to relate to business models. Are you talking about having a few very centralized, very large facilities? We're talking about having more facilities that are each specialized in doing different things, right? Because it's really hard to get that balance between scale and flexibility, right? It's if flexibility is about the variety of projects you can take on, as opposed to just doing the same thing over and over again, which is, I think, in practice, what's being asked of these platform facilities, or how at least they've presented themselves, then it's harder to achieve sort of scale. Right. So here are a couple of academic biofoundry practitioners who are really grappling with this a couple of years ago at the annual meeting of their consortium. And they're like, the power in theory is doing the same things over and over again. But if you have 20 people knocking on your door and they're all asking for something slightly different, and you're constantly having to adapt your workflow, you lose the power of the foundry, right? And so this is, again, like, how do we allow ourselves to be both flexible in the projects we take on, but also scalable, or like, how do those things meet? And also gets deep into the models, like, how are these biofoundries imagined to work? So these foundries, like, yeah, we set ourselves up, and then you realize, like, people come in and they're not all working with E. coli, they're working with all kinds of organisms. And then you have to decide how much work, again, am I going to put into developing a workflow customized to that organism, because biology is more idiosyncratic and sensitive than we might want it to be. And if your model of your biofoundry is that you're going to survive on multiple smaller contracts, it's really hard to turn those down, right? Like if scale is about diversity and user base, it's hard to turn these down, but then the cost of onboarding a project who bears that cost basically becomes a core question for these foundries. Because if you just go to the user and say, hey, this is the cost of like getting your workflow up and running, as well as then delivering your products, sticker shock. Right. And maybe the time that it's going to take to do this and so on. And so if you're wanting to enroll a user base and say, don't do this in your lab, we can do this for you faster and cheaper and easier, you have to actually like make true on that. But in this case, the Biofoundry itself is absorbing a lot of that work, right? So it has implications for how you build your market and the kinds of contracts that you take on. So across the Biofoundries that I visited, the ones that have like one or two major projects that are really well funded, that are kind of really targeting one or two core things, are far less stressed than the Biofoundries that are sort of trying to take on multiple different projects from smaller projects and satisfy them all, but they're also absorbing all the costs of onboarding, right? And so there's an anthropologist called Anna Singh who has talked a lot about this relationship between of how you scale. And she has this piece on non-scalability where she says, at best, scalable projects are articulations between scalable and non-scalable elements in which the non-scalable effects can be hidden from project investors, right? So it's sort of like, there's always non-scalable. And it's sort of, what is the non-scalable? How does it manifest? And, in the interest of scale, like, what is it that what are the non-scalable parts that you put to one side? Which I think takes us nicely into the question of work and the work that's done in the kind of work that gets done in these facilities. Remember, because it's all about, in principle, reducing error, de-skilling the work, freeing up people's time, right? So I'm going to talk here about work that two grad students have done. They both kind of raise different concepts, which I think are both fun and provocative to think with. So Chris Mellingwood studied two academic biofoundries for his PhD and kind of came to the conclusion that the skills that these biofoundry practitioners had, he said they were amphibious in nature. And by that, he talked about their comfort in being able to move and live in both wet and dry environments, right? So they basically had to have an incredibly deep understanding of the machinery and the equipment and all its idiosyncrasies and how it worked, as well as an understanding of how the biology would engage with and interact with that equipment in order to successfully design and complete workflows, right? So I think it's a really kind of nice idea to think with. And again, if we're thinking about implications for workforce development, Chris raises this question of like, at what point would we be able to dispense with this kind of amphibious knowledge, right? Would we get to the point where biology is really black boxed? Or are we still going to need some of this deep understanding of how the biology will interact with the machines in order to get to where we want to go? Annie Hemang, she actually started after her undergrad degree, she went and worked in a commercial biofoundry for a couple of years and then moved into a PhD in anthropology where she studied she studied commercial biofoundries. And she came up, she was interested in kind of the working lives of biofoundry practitioners, but from a slightly different angle to what Chris was looking at. And she came up with, I think, again, this really provocative idea of routine interruption, which is really trying to get at what it is that biofoundry workers experience or machine operators experience. So she says, in an ideal world, a workflow looks like this, where you have multiple discrete steps and you have samples and information moving seamlessly from one to the next in a very linear fashion. And she said in practice, in her working life and in those that she engaged with during her field work, the process looked a lot messier, where some samples clearly moved through the system, but others were, had to be passed back through, or there was some like messy troubleshooting that had to be done. Sometimes she talked about the guardian angels that had to be brought in to try and figure out if it was the machine or the biological sample or what about it had gone wrong. But she said that basically the work was characterized by this routine interruption, right? This unpredictability, so predictable unpredictability in whether something would work. And that's actually a reasonably stressful state to be in as a practitioner, especially because you have to make it look like it's all going down as the top picture suggests. So Annie started getting interested in this and said, actually, so one of the things, it's amphibious skills, but also troubleshooting skills that come to the fore in biofoundries, especially when we're setting them up. And so she said troubleshooting is this new form of highly skilled work, but there's a fundamental problem with troubleshooting, which is that it's work that by its very definition is problematic and should be erased, right? Like it's work that you want to have go away. So you don't want to talk about it. You don't want to highlight it. You don't, want to make more of it. But by doing so, what you're doing by kind of erasing the labor of troubleshooting is you're devaluing the work of those troubleshooters, right? Which becomes an ethical choice because you're trying to make it look like the platform is working, but you're also then not valuing in a profound way the deep amphibious expertise that it takes to really troubleshoot what's going on. All right, super quick, a little bit about time, and then love to have some discussion around all this. Okay, so I'm just gonna say kind of one quick thing about time, which I think is this kind of really interesting set of considerations that are emerging around sort of how you choreograph biological time and machine time in Biofoundries, right? So again, these slight reconceptualizations that are taking place. One of the key concerns when you've spent several $1 million on robots is how to use the robots well, right? How to use them as efficiently as possible. In a lot of the foundries that I visited, there's actually more concern right now with the underuse of robots than the overuse of robots, but still really trying to figure out how to use them most efficiently, right? And so the idea of batching an experiment, of batching work, for example. So the unit of work is no longer the individual project or the individual experiment, but the batch of materials or samples that can be processed at any given time. So it's a slight conceptual shift away from thinking about your own single experiment to how you can basically prioritize the needs of, or the desire to use the robot well, right? But of course, biology is very temporally sensitive. So you can't just do what the robots want. You have to also really be sensitive to what the biology needs, right? So you kind of get into this territory of really having to think carefully about the kind of dance between the biology and the robots. And so there's a lot of emphasis in foundries as well on trying to figure out through software in particular, like how do you schedule, how do you batch, how do you pull together, how do you actually ensure efficient flow of samples and material through the foundry, right? So again, and this is software, this isn't seen as much, right? It's not visible in the robots and it's not, the working lives, but it's like actually built into the kind of the management system that sort of, manages the flow of information through the foundry. And this is again, going back to what I was saying about, a lot of my interests are really trying to think through like, how do decisions at the lab bench reflect out in bigger ways? What are the implications of those things? This is just another example. I hope I've provided kind of several examples of that, but this is another example where you can say, interrogate what the software is doing and what the software is prioritizing. So when it's making these choices, right? Or it's kind of making these design choices, what is it prioritizing? Is the default to prioritize the robots? Is the default to prioritize the biological samples, the default to prioritize the worker, or in what combination, right? So this is, again, a place where you can see how technical decisions end up having ramifications that play out in the actual operation of the foundry itself. So yeah, just to sum up, I think, for me at least, hopefully I've managed to share with you some of this enthusiasm. I think that Biofoundries are this really interesting kind of experiment, a very lively site at the moment for working through a variety of challenges that I think are all relevant to the bioeconomy in different ways, right? So there's sort of one site, it's not the only place, but there's sort of a microcosm of some of the things that we should be thinking about as we try and develop this sort of increasingly bio-based economy. So there's questions around disruption of biotech sectors. Like, what does that look like? How might, is that what we want? Or like, how are biofoundries fitting in there? I think one thing that becomes really clear spending time in these places is that we really need to acknowledge the investment needed to move across scales. And that's not just financial investment, but it's expertise as well, right? And time. And that sometimes, we have these sort of shareholder demands, or we have these senses of like having to do things really quickly, but that this isn't just a straightforward manufacturing situation. This is actually about developing foundational knowledge that's reconceptualizing how we think about biology, how we think about experiments, what a workflow looks like, and so on. And that within these workflows that we're developing, there are different values that can be embedded in them. So for example, if I gave you the challenge of saying, okay, design a workflow, this one needs to be done as quickly as possible, versus this one needs to be done as sustainably as possible, versus this one needs to be done in such a way that it can accommodate wide diversity, right? So scale in a different way. Like those workflows would look different, right? So kind of as these workflows are being set up, being very attuned to the kinds of values that we're promoting, and again, how that sort of ricochets out into what sort of bioeconomy we might want. I think there are clear implications here for like workforce development and jobs of the future in terms of the kinds of skills and expertise that are needed. Clear struggles around how you create and enroll a user base, right? So how do you convince clients to come and make use of your workflows that have yet to be constructed or meet, right? And then how do you enter those supply chains, right? Because you're reconfiguring them. It might sound like a straightforward substitution, but you're coming in and displacing a petroleum-based product with a bio-based one, and that's not necessarily a seamless task. So I think a number of things where we can see this as a microcosm for how some of these challenges might play out. So just to thank the European Research Council and the National Science Foundation and the ASU Institute for Social Science Research for sponsoring, supporting some of this work and some of my students. And to say, yeah, I'd love to have conversation, discussion with you about this, and whether any of it resonated, I'd be very curious to know.